Hello, everyone. I'm trying something a little bit different this time, so we're going to hope that it works okay and that you can see everything. So today we're going to be talking about section 1.5, and the topic is continuity. That's an excellent spelling word. So the first thing I want you to do is to think about what does it mean to you when I say the word continuity or continuous. What does that mean? So I think I'm going to try this. Let's see if it works. Okay, there's my screen. Let's see this, right? Here it is, continuity. The unbroken and consistent existence or operation of something over a period of time. Okay, that's really what we're talking about when we're dealing with continuity. Now, hopefully, let's see, hang on. I have to figure this out. Okay, it's good. Couple things about the video. So we're going to start this way, and I have a pad of paper behind me, and I've already got a lot of stuff written. So I'm not going to slow down to let people write stuff down. If you need to, pause the video so you can get stuff written down. That's great. Do that. Also, this will only allow me to record 15 minutes at a time. So you're going to have several videos to watch. So watch them in order or else they might not make any sense. I think I've got them in order in Canvas, so that should be good for you. I don't know how many videos it's going to be because I don't know how long this is going to take, but it's a bit. So let's get started. Here is the little pad of paper. I'm going to move this down so we can see. There we go. Continuity. So we already thought about the word continuity. And what we're going to find is that sometimes there are breaks in a graph. Oh, okay. Yeah, sometimes there are breaks in a graph. So I've drawn 4 graphs here where you can see we have breaks in them. This one, it might be, let me see if I can zoom in on it. Zoom, if you can only see what I'm having to do this right now, right? You can see that there is a hole in the graph at x equals c, okay? On this one, we have a break in the graph at x equals c where it jumps from one curve to the other. Okay, on this one, we have an asymptote, and then it's got a dot on the asymptote, so it's been defined there, but yeah, you can tell that's not continuous, right? I can't put my pen on the curve and draw all pieces of the curve without having to pick up my pen. Okay, that's the deal. And then this last one here, we've got, again, another break where I would have to put my pen here, go up here and draw this dot, and then come back and draw this one. So again, not continuous. Sometimes this happens with functions. I don't know how this is going to work. So here is the definition of continuity. I think that's going to work. Is that? Yeah, I think so. Yeah, I think you can see that. A function f is said to be continuous at x equals c if there are 3 conditions. Number 1, f of c has to be defined. Number 2, the limit as x approaches c of f of x has to exist. And number 3, the limit as x approaches c of f of x has to also equal f of c itself. And then really these 2 statements say the same thing. All conditions must be true for continuity. If one or more of these conditions fails to hold, then f has what we call discontinuity at x equals c. That's another fabulous spelling word, discontinuity. Nice. Okay, so actually, hold that thought. I want to come back over here. So let's kind of think about our definition with respect to these 4 graphs that we have and see if we can figure out which conditions that these violate so that we'll kind of understand what we're talking about with continuity. So if we look at this graph, okay, this one has, it's pretty good, right? We come up here, but then we have a hole in the graph and then it goes further. And so what we find is that f of c is not defined, okay? So I'm going to write that f of c is not defined. And I might write up here, violates condition 1. Okay, f of c is not defined there, so that violates this condition. The second graph, right? F of c has to be defined. Well, in this case, f of c is defined. It's this point right here. Okay, so that's fine. The limit as x approaches c of f of x has to exist. And remember, for a limit to exist, we have to be able to approach some value from the left and approach some value from the right and have them meet. These do not meet. Therefore, the limit as x approaches c of f of x does not exist, okay, on this one. And so this one violates condition 2. Okay. Next, we need to talk about this graph. So we have, is f of c defined? Well, we can see here's c. F of c is this dot right here, so it's defined. Does the limit exist? As I approach c from the left, this is going towards positive infinity. As I approach c from the right, it's going towards positive infinity. Since the left and the right-hand limit match, the limit does exist. Okay, so the limit exists. Now, this wants to know, does the limit as x approaches c equal f of c? Well, the limit as x approaches c of this one is positive infinity. And f of c is some value here. We don't really know what it is, but it's some number, and it's not positive infinity. So f of c is some number. The limit is positive infinity. Therefore, they are not equal. Okay, so we'll say up here, this violates condition 3. And the last graph over here, can we see it? Let's get a little bit better picture there. Okay, we have, first of all, is f of c defined? Again, we have a point here, so yes, f of c is defined. Does the limit exist? So again, coming from the left and coming from the right, okay, they come to the same, they meet, and so the limit does exist. However, the limit, which would be this value, right, I'm going to write limit over here, right, and this would be f of c. Okay, so the limit is one value, f of c is another value. Oh, I don't know if that's really hard to see. Can you guys see it? Whoops, hang on. Okay, there we go. Right? So the limit is one value, f of c is a different value. Therefore, this violates condition 3 as well. Okay. So as you can see, all of these things have to be true in order for continuity to happen on a function. Okay? Okay, now I think we're ready to turn the page. Okay, let's scoot this up again. I don't know, I can't decide if I like this or not. It may change before the next video, we'll see. Let's scoot this in. Extreme close-up. Nope, wrong way. Hello. There we go. All right, determine if each function is continuous at x equals 2. Okay, so we have this function, f of x equals x squared minus 4 over x minus 2. So the first thing that we need to decide is if f of c is defined. Oh, all kinds of crazy stuff going on here. And what we're going to find is that when we try to find f of 2, we'll have 2 squared minus 4 over 2 minus 2, which is not defined. Okay, So this one is not continuous at x equals 2. Okay. All right, next we have g of x down here. We want to know again, is this function continuous at x equals 2? So we need to think about a couple of things. First of all, we need to know if f of 2 is defined. Well, this one's actually quite interesting because we have this function, same one that we had up here, when x is not 2, but we have a value x equals, or g of x equals 3 when x is exactly 2. So f of 2 is 3. So f of 2 is defined. Okay? Then we need to know if the limit, so that's condition 1. Condition 2, does the limit as x approaches 2 of f of x exist? Okay? And we can think about that by using our normal limit procedures. Okay. So normally I would think up here, and we can see back at this problem, we would have gotten 0 over 0, which means when we're looking for a limit, do something else. That do something else generally means factor, right? So I might call this the limit as x approaches 2 of x plus 2 over x minus 2 divided by x minus 2. I factored that difference of squares. We can cancel. So therefore, the limit as x approaches 2 of x plus 2 is equal to 2 plus 2, or 4. Okay, so the limit does exist, and in fact, the limit is 4. Okay, so f of 2 is defined. The limit as x approaches 2 exists, and it is 4. Question number 3 says the limit as x approaches 2 of f of x needs to equal f of c, or f of 2 in this case. And I'm going to put a little question mark above that equal sign. Are they the same? Well, this limit, we found it, it's 4. Does 4 equal, we defined this, it was 3? No. Okay. So now we'll go down here to the bottom one, h of x, and you'll see that this one has a little bit, something a little bit different than the last one, okay, where we've got, again, the same function, but now when x is equal to 2, we've defined it as 4. So f of 2 now is 4. Number 2 condition, the limit as x approaches 2 of f of x. We already found it. We did it up here. We don't need to reinvent the wheel. It is 4. Number 3, does the limit as x approach 2 of f of x equal f of 2? 4 equals 4. Yes. Okay. So this wanted us to determine if any of these functions were continuous, and what we were able to find was that sometimes, even if we have just a regular function and it is not continuous, we can do things to help us create continuity. And in this case, it meant redefining our function a little bit, and a little bit more narrowly this way with part C. Okay? All right. Next. Let me turn the page. Oh, let me check my time. Oh, I'm going to have to stop this video because we're at 14 and 15 seconds. So I'm going to stop this one, and then I will start up again with the next little topic, if I can find the pause. Oh my, where's the cursor?